And with no further ado, let's go to the next panel. The next panel is going to be led by the one and only Crystal Johnson. Crystal's been serving as the Deputy Center Director here at Goddard for Research and Technology and is now on an assignment to the Administrator's Office on working on that digital toolbox and the translation of how NASA interfaces on the front door. So Crystal, you're up, and I'll let you introduce your panel. Knock it out.
Absolutely. You all come on up. Wonderful. All right. Thank you. Well, hello, everyone. Good afternoon. Are we awake still? Yes, very good, actually. So thank you very much, Charlie, for the introduction that you gave here. We are very excited to bring a little bit of a different spin on a panel that we have here. So I'm Crystal Johnson. He mentioned my day job, my normal day job, but I am on detail going to the Office of the Administrator to work full-time on 2040. And is there anybody in this room that doesn't know about NASA 2040? Anybody? Right, so I think we all know that by 2040, at this point in time, the agency's trying to figure out what does NASA of 2040 actually need to look like? You know, what does the mission really need to look like? What is the structure? How should we be organized? What kinds of people training do we need? What kinds of technology should we be investing in now in order for us to be ready to have humans living sustainably on the moon by 2040? And for us to think about the technology aspects of that and all of the digital toolbox elements that are going to be necessary for that, thinking about, you know, all of the medical aspects of humans living sustainably someplace else, being able to have sensors on and about the body to really be able to know what's happening inside the body. For us to look at all kinds of things like the environment and being able to have clean drinking water and being able to have food and all of those things in a sustainable way where you have no gravity and lots of challenges that we face. And so as we think about the future, we're looking at all of the tools that we're actually using today that are making a difference and that we're going to have to actually put on steroids to get ready for 2040. And thinking about the toolbox that we've got today, one of the major elements within our toolbox is AI. And as you know, we're using AI for so many different applications that are helping us in just the small ways that we live life today. And there were quite a few discussions in the last panel that we can actually expand on using some of the AI tools that we're thinking about today. And so as we're thinking about the environment and agriculture, Karen St. Germain mentioned that we do quite a bit of partnering with the agricultural community. And we think about farmers in a very kind of myopic way, but they are very, as she said, digital and data heavy. They really need to look at the yield. So they have drones and satellites, and they take some of that information and it helps them to predict or to monitor the health and the welfare of their crops. Also to really be able to predict when, you know, they have when they're infested with pesticides and things like that. And so there are a lot of ways that they are going to be able to use that data to be able to help. And as we design our missions, model-based systems engineering approaches are going to be absolutely critical. Iterative design, being able to make changes to your system very rapidly, and at the end of that iteration, be able to have something manufactured that's easy for the manufacturers in terms of the materials and the designs that we end up coming up with. And so there are so many other areas. You think about enterprise data management as well. And what we're getting to is a real digital ecosystem, which means that we have several IT systems that function as one. And when you have several IT systems that function as one, then of course you have the concern about security. So cybersecurity is another very important element to what we're doing. What you certainly don't want to do is open yourself up to a lot more vulnerabilities just so that you can have an interconnected world. And so all of those elements are things that we really need to think about. So this particular panel is going to be diving a little bit into a few of the digital tools in our toolbox. And we're taking a different approach. It's not going to be just kind of us sitting up here talking to each other. We are taking an approach of being able to give you actual demonstrations from two of our partner organizations that partner with us here at NASA. And so I'm going to introduce the panel members first. Andrew Sullivan over here. He's going to give a demonstration. So Andrew is the program director at SAIC. He is a visionary leader, project program manager with extensive experience in systems engineering, integration, modeling, and simulation. He has led technical teams in the areas of communications and networking for 19 years for both satellite and terrestrial systems. He has supported Army and Air Force customers extensively and has established their trust through subject matter expertise, hard work, and the ability to effectively communicate. And he loves the communication part. So anytime anybody wants a digital engineering demonstration, he's on it. So let me turn it over to you, Andrew. Thank you.
Okay, great. Okay, can everybody hear me okay? Going to project from my laptop. Okay, fantastic. Well, thank you, Crystal, and thank you for the opportunity to present here to you all. I'm new to this community. I've come from Air Force, Space Force, satellite, more on the defense side. This is just a fascinating conference, and I appreciate the opportunity to be a part of it. So what I'm going to talk about today is the application of digital engineering to an Artemis walk-back mission. And I'm going to start by defining some terms. So digital engineering means different things to different people. For the purpose of this presentation and my experience in this area, digital engineering is a term that I use to bring together traditional performance-based modeling, think physics and math-based models, and model-based systems engineering that Crystal mentioned. So that's thinking about architectures, requirements, interfaces captured in a digital model. So as you bring those two together, that discipline, again, for the purpose of this, is called digital engineering. So here's the esteemed team that I've got that's responsible for the development of this. I'm merely this kind of the spokesperson of it. But what I'm going to be talking about today is the value of these tools as you apply them to challenging problems. In this case, an Artemis mission that we'll get into in a moment. And so being able to capture systems and address hard problems in these tools allows you to do exploration and trade studies, assist your engineering activities in ways that were unavailable to us, a couple decades ago. And so as people have been moving more digitally, you're seeing increasing amounts of these kind of technologies and capabilities. So we're going to talk about the advantages towards mission integration, planning, even training as we go forward. So here's an example of the configuration that I'll show you in a moment. We've got the architecture that's captured in a tool called Cameo, Enterprise Architect. That's in the upper left. And the kind of top middle there, you'll have the virtual environment that we're going to spend most of our time in. And then all this data is getting pulled right now from a cloud environment that we've got running. I'm connected through the Wi-Fi. It's into an SAIC cloud where you have these tools running there. And so as we go through this mission, what you're going to be seeing is that you've got a lunar terrain vehicle that's going to be proceeding across the surface of the Earth. It's going to encounter a mishap. That's going to force the astronauts to walk back. And there's going to be some tools that are going to come alive that are going to give them the ability to help make some decisions about how to successfully prosecute that. Can I grab my water? Thanks so much. 6-inch step to your left to stay in the light. There you go. Okay, thank you. So some of the things that we're going to be demonstrating is that the fact that we've got a high fidelity representation of the lunar surface using the LRO data, the Lunar Reconnaissance Orbiter data. We've got we've got astronauts that have data that's coming off of their suits. It's being computed in one of the tools and kind of displayed in the other. We're going to have the ability to interact with this digital twin of the lunar surface, as well as being able to understand more about the situation by having a multi-perspective set of models there. So traditional modeling, for example, about a year and a half ago, when I started doing this kind of work, we found that most of the digital engineering work we had was tucked away in a lab somewhere. It was computations running on some computer. Being able to bring that out sort of into the daylight and creating more interactive experiences for people has increased the value of this benefit for all the customers that we support. So here's an example of the architecture. It's in a tool called Cameo, and you can see kind of on the left-hand side, you've got the vehicle and its various subsystems. On the right-hand side, you've got the crew segment, the suit, and all the subsystems there. So one of the important parts of this is that each of these blocks that are represented here, we have them all running in a single model, but they could be integrated as either models from other vendors or hardware and software that's represented that represents those models, coming from various places. So you could have hardware in the loop, software in the loop, other models all brought together in a system of systems to perform this mission integration function. So the important part is when you've got different OEMs delivering different pieces, you often don't have an easy way to stitch that all together and do system of systems level trade studies that involve each of these constituent parts. So this is a capability that allows that. So what you're going to see is a realistic Artemis scenario that links dynamic model-based system engineering with visualization in a multi-perspective tool that allows both operations planning and training and other benefits that we'll talk about. You'll see that we're basing this on the LRO data. We've got computations that are captured in the Cameo model for consumption rates for oxygen, battery, and other factors. You've got also seeing the power of digital engineering orchestrate the mission integration function is part of what you're going to see. So I'm going to jump out of that PowerPoint and go into, it's an Amazon Web Services cloud that we're going to pull up. Here's an example of the Cameo model that I'm showing, and I've kicked off the simulation here, and so we won't explore this model in detail, but you can see that it's here and running. I'm in a lower console. You can see I'm awaiting a command. I'm going to turn it over to the Unity 3D, which is a video game engine. And this is a technology that's used to create more immersive experiences as kind of a front end to this digital twin. So I'm going to kick this off. You see it's about to start. And what you're watching now is not a video. It's basically, think of it almost like a video game. It's the tool that's running. It's kicking off, and you can see Neil and Buzz in the upper left there with their kind of consumables. There's a little display there for it. We're kind of zooming in on the habitat here in a moment, and you're going to see some kind of factoids that are going to kind of scroll across the bottom of the screen talking about the scenario as we go through. So the goal of this particular excursion is to take the lunar terrain vehicle out about 10 miles from the habitat area to go collect some samples. And so part of what we're not going to get there because we're going to have a mishap, as you'll see in a moment here, but we had to make some assumptions about what was kind of in place. Not everything is explicitly modeled. In fact, this technique was adapted from a missile warning and missile tracking model that we applied similar technologies as we're trying to bring different pieces of a mission together. So we've assumed that there's working comms, that there's the ability to sort of know where positionally we are throughout this. So we've got things like, in addition to the terrain that you see modeled here, we've got things like the moon's gravity captured. So the way to think about the modeling elements of this, the Unity 3D software that you're seeing here has the terrain. It has basic physics in it for how, for example, how the elevation is going to interact with the rate of consumption of oxygen and water. Whereas Cameo has got a lot of the detailed math models that are captured. So there's interactions happening back and forth between those tools, all kind of behind the scenes. So at the time of the breakdown, Cameo is going to be used to calculate the optimal path back from the wreckage to the habitat, which you'll see here in a moment. The guys are driving a little crazy. You can see they're catching air off of some of the jumps. You've got moon gravity there, so it's a little more exaggerated than normal Earth driving. So as they're coming around the corner here, they're going to hit one of these potholes, and they're going to take a dive. So we certainly don't encourage this sort of driving, on the moon. But if you find yourself in a situation like this, you'd like to have one of these tools available at your disposal. So now what happens is you're looking at a top-down view of that same situation. I can toggle between sort of the crash site, if you will, and this sort of little tool. Think of it as a mission planning tool. So the green little icon is where we've landed. The red icon is where we want to get back to. So think of this, even though this is a digital twin of this situation and a simulation, there's also mission planning and training opportunities kind of available here. So if I click on draw, and then I draw a path, let's say you've got the ability to say, hey, I think I remember the way that I got here. I think I could manually create a path back to where I need to be. So here I am kind of drawing a path back. And what this does is it calculates the route length and the average grade, as well as you can see here, the sort of change in elevation over the whole course of the journey. I'm going to draw another path, and I'm going to exaggerate. It's taking a really windy path through a couple of craters. Again, not advisable, but you can see there that this sort of also produces real time sort of what the terrain looks like to give you an idea about, hey, what am I in for here? So back to Crystal's point about AI, we built in some AI algorithms in here that can also calculate a path based on a variety of factors of your choosing. So if I click on Find Path, what that does is it goes and calculates a path based on things like change in elevation, amount of shadow that I want to avoid. If I've got solar abilities in my suit, I want to make sure I keep it in some kind of sunlight. I can avoid those, and so it can route a path based on all that. So it's calculated a path for me as well. Once I get at least 3 paths calculated, I then go back to Cameo, my architecture tool, and what that's going to do is say, hey, you've given me 3 options. I'm going to give you the best of the available options based on some computations and optimizations. So it spits back that data, and then it's selected for me that particular path, the path 0, which is one of the ones that I drew. So then if I say, hey, I want to use that path, I do that. Now, ever so hurriedly, the astronauts are running. For the purpose of time, they're going very, very fast. As we toggle back, you can see also the consumables in the lower right sort of decrementing, and you should be able to see this kind of traversing this path as well from where they were to where they're going. So, and then the kind of estimated time remaining. So you can see them still hustling here, trying to get back to the habitat before their oxygen runs out, not helping as they're breathing more. But this is an example of being able to have the abilities to deal with different kinds of situations. You want to have the tools in place to be able to plan for what if something happens? What if something unplanned happens? Do I have the ability between, think about this kind of capability either on the habitat, on the LTV, on the astronauts themselves through some kind of tablet that they're able to navigate their way back and pick an optimal path. Then you see the kind of consumables there sort of continuing to sort of deplete as we go forward. So, and then if I go back to sort of get off the stage here, let me just expand that. Some of the things that we hope you took away from that are the value of capturing something like the Artemis architecture in a model-based system engineering tools. Some of the benefits you get from that, just that people are very familiar with, are being able to capture your requirements, your architecture, your ConOps, be able to generate interface control documents and technical requirements documents, interface specifications for other vendors directly out of the tool. You push a button and then it spits them out if you've got the requisite data in the tool. One of the things that we've done here by leveraging the capability of Cameo simulation, which not everybody uses simulation built into some of these architecture tools, you get this interactive ability to do things like kind of what you saw here. So you've got the Cameo running a simulation, you've got this virtual reality tool, Unity, and you've got, for those familiar with it, JSON, JavaScript object notation technology to kind of pass data between the two. So we show the ability to enable the integration in a multi-vendor OEM kind of environment to create a structure to bring those pieces together and to do system of systems level trade studies by being able to incorporate the key elements of those different systems. So you can come up with optimal solutions, saving you cost, reducing risk, and doing this well in advance of when you would be writing software, bending metal, giving you an advantage over time. And then being able to sort of control this. In the early version of this, we had people actually driving around the moon, you know, with VR headsets on. So I mean, that's another aspect. You actually have astronauts or other people in this environment experiencing it as they would if they were actually on the moon, which again creates not only a phenomenal training opportunity, but getting operational input well in advance of the design allows you to think through things that you wouldn't think about, you know, until perhaps at the end of the design in a traditional acquisition. And then lastly, that multiple perspective. When I've done this at other conferences, I've had multiple screens, 3 or 4 screens, and each element kind of running simultaneously on different screens gives you a really interesting perspective. Since some people, if they're an architect, are going to sort of gravitate towards the architecture sort of screens, boxes and lines. Someone else is going to gravitate towards the operational view. Someone else might look at sort of the physics-based view. And having all those running simultaneously really opens up a rich dialogue to be able to get feedback and improve the process. So that's all I was going to present today.
All right.
Thank you.
Thank you very much. Thank you. All right, and next we have Lynn Montgomery, who is the AI research engineer at Lockheed Martin. In this capacity, she's the AI ML research team lead on the Cognitive Mission Management Program, which uses AI ML to map, predict, and provide course of action recommendations for wildfires. And she's the PI and technical lead of the AI-based Earth and Space Observing Digital Twin prototype for NOAA. Today, we'll be getting a demonstration of the work she's doing with this digital twin prototype.
Thanks, I appreciate it, Crystal. And yeah, that was really awesome, Andy, to see that digital twin. That was very, very cool. But yeah, so I'm an AI research engineer at Lockheed Martin Space, and today I'm going to be telling you about our AI-driven Earth and Space Observing Digital Twin. And I just wanted to take a moment. This is a large program. We have a lot of software engineers. We have a lot of AI research engineers. We have a lot of program folks who help us out. So this is certainly not a singular effort. And then do we have the clicker?
Should be up on the podium, maybe? Up on the other side. Yeah. And push the down arrow to advance.
Thank you.
Yep.
Great. Okay, so this is a 2-year program between Lockheed Martin and NVIDIA to build a digital twin prototype for NOAA for the Joint Ventures Partnership. And this prototype is going to be for demonstration and study purposes. So there's multiple different types of digital twins. It's a bit of a buzzword right now. Some people use digital twins in order to work on manufacturing plants to see where you would put certain machines in order to do certain things at certain times. Other people use them in order to build satellites and models before they launch a satellite into space on a computer. And what NOAA NESDIS Joint Ventures was looking for was to reach out and see what the community was doing with digital twins and if someone could build them a prototype in order to look at current environmental conditions. So we're looking at current conditions as well as 2 weeks past. And we are looking at a variety of different Earth system domains. So we're looking at the atmosphere, ocean, cryosphere, which is polar regions, land and hydrology, and space weather. And for this prototype, we're looking at a geophysical variable to build out for each of these different domains, including 3D temperature and moisture profiles, sea surface temperature, sea ice concentration, fire products, and solar wind bulk plasma. And so we're going to be gathering observations from these, from ground-based observations as well as space-based observations from some of the satellites here, including GOES 16 and 18, JPSS, and Discover, as well as model output coming from the Global Forecasting System. We're looking at a global system, so right now we're looking at a 10-kilometer spatial resolution and an hourly to sub-hourly temporal resolution based on the contract. So this is a quick look at our framework and overview of what we proposed for this 2-year program. So again, we're ingesting satellite data, ground-based data, and model data. Our backend framework is called Open Rosetta 3D, which is a TRL9 software product that we're adapting for this specific use case. So we're able to do data storage management. Right now we're using AWS for all of these services. However, it is cloud agnostic. We apply a common spatiotemporal grid to that data coming in. We then look at fusing the data as well as looking at anomaly detections with the data using machine learning algorithms or other algorithms if you don't need to use AI. We then transition that data to Omniverse Nucleus, which is NVIDIA's part of this program, which serves as our central data storage and distribution. So this allows for interoperability, which was talked about a bit on the last panel, in the sense that we're building out this digital twin prototype for NOAA, but NASA's building their own digital twin, and ESA or EUMETSAT is building out their own digital twin too. So if they don't want to go through our back end, then we have Omniverse Nucleus where you're able to plug in your own digital twin to it so that we would be able to combine that information there more easily. And then finally, we have our UI, which is called Agatha, and it's a 4D global visualization tool. So it's 3D in the sense that we have a global view of it, and it's 4D in the sense that we have that moving 2-week time window for those current environmental observations coming in. We want to highlight that for this program, since we are trying to interoperate with multiple different digital twins in the future, we're trying to make this configurable as possible, as scalable as possible, as flexible as possible. So a cool part of our backend is that we are able to ingest most algorithms. So what NOAA is doing right now is sending us their algorithms. We're able to containerize those, and then we're able to plug those into our backend dynamically. So we basically have a plug-and-play architecture that we're able to use for those algorithms, whether they're machine learning or traditional. Finally, just a few use cases here. So our first use case is for research scientists in the sense that they would be able to use this platform at NOAA or NASA in order to work with their own algorithms and not only visualize the data, but be able to export the data for their use cases. The other main use case is that it's a platform to combine all of these disparate observations coming from different sources to kind of create this one-stop shop where we can fuse those data sources together to create a more granular data set for initialization of models. Because if you know what's happening right now, then you'll be able to predict better in the future what's going to occur. So it can help those forecasting models by having this platform that's able to combine all of those observations together. And then finally, right now we're only looking at monitoring with this digital twin. So again, current observations, but in the future, hypothetically, this could be expanded to what-if simulations as well as predictive scenarios, although we are not doing any prediction currently. So we will jump into our demonstration here. So this is our UI called Agatha. Right now you're looking at sea surface temperature from the GFS, and you can see the diurnal cycle, so it's getting warmer during the day and cooler at night. You can see that we have metadata at the top, so we have temperature, latitude, and longitude for location, as well as a timestamp to determine the time period. Again, this is 10 kilometers globally for our spatial resolution and hourly for our temporal resolution. And you can see that we have a color bar in the top right, so it's in Kelvin right now, going from 273 to 310 degrees Kelvin. We'll transition over to GOES, which is a geostationary satellite, and this is showing the full disk for GOES East right now. So you can see that some data is missing because we filter out clouds with that. And then we're going to go over to GOES West. So similar to GOES East, it's geostationary, just pointing at a different area of interest. We can then transition to VEERS, which is a polar orbiting satellite, so we'll just see a small snapshot of data instead of a full disk or instead of globally gridded. We then transition to the fused data, so we're bringing together those disparate sources of GOES West and East, as well as GFS and VEERS, and we are statistically downscaling those to that common 10-kilometer resolution. And then we'll transition over to our anomaly detection. So this is the difference between the fused data and the previous hour of the GFS that we're treating as truth because that's about as close as we have right now. So you can see that the temperature difference transitioned to -1 to 1 degrees Kelvin. So, that's a pretty normal range of difference within an hour for sea surface temperature. If you saw anything higher than that, you'd probably want to bring a human in the loop to determine if that's a sensor anomaly or a physical anomaly. And then you can see it moving over time as well. We also wanted to highlight that we have a dynamic color map so that you're able to change the gradients to look at what you want. And we're actively working with NOAA to make sure that these color maps are intuitive for them and their scientists so that they're what they expect. Now we're showing our 3D temperature and moisture profiles. So this is specific humidity data coming from the GFS. So you can see that we have global data for it over both the land and the ocean. And then we have this data at different vertical levels. So we have it at the surface at 1,000 millibars, And then we have 3 other different levels that we're looking at, including 750, 500, and 250 millibars. So you can see some synoptic scale patterns there as well. You can also see at the higher vertical levels, we have missing data because you no longer have that data at the surface. So for example, here, where there's mountainous regions, you no longer have that data there, since we're at a higher vertical level. We also just recently added in a feature to show the continents over it, so you would know where you are on the Earth. This is for our temperature. So similarly to the specific humidity, we have data coming from the surface at 1,000 millibars, 750, 500, and 250 millibars. Again, you can see some synoptic scale patterns as well. And so our contract has about 6 months left. We have the majority of the data ingested into our model. However, we're working on getting everything fully visualized into our system here. So we're really excited to have just integrated our 3D data, and we'll be moving on to additional data sets soon. So yeah, excited to be part of the panel. And
Awesome.
yeah.
Thank you very much. Let's thank her. Yeah, so the digital capability that you all are seeing here for me is really, really exciting because it's so empowering. It's going to cause us to be able to see things that we've never been able to see before. The volume of data coming back down from Earth is growing exponentially. And so you think about Hubble. Hubble had 2.7 gigabytes of data coming back down to the Earth daily. Then you go next step up to James Webb. We've got 58 gigabytes of data coming down daily. And then you think about Roman. By the time we've got the Roman data coming back down, 1,375 gigabytes per day coming back down. And being able to have digital tools like this that take multiple observations and combine them to help us to see things that we've never been able to see before is going to be incredibly powerful for us and will take us to the next level. So for you, Lynn, the first question that I have for you is how are you using artificial intelligence? How is that being leveraged to build, update, and analyze these digital twin models to really update them and make them even more powerful than they are already today?
Absolutely, yeah. So in our particular model, we're using AI and we're able to plug in particular algorithms that scientists are using. And often these algorithms are able to speed up from traditional algorithms. So for example, in the weather forecasting community, right now the majority of the weather forecasting models are in Fortran. And that's been used for the majority of the past, but for right now what you can do is use AI models in order to kind of make connections between traditional variables, like let's say for example you have temperature, and you're able to derive a different quantity from that. You can train the AI models in order to be able to make that relationship more quickly than using a traditional physics model. And so in the future, that would allow us to be able to make decisions faster and be able to provide risk assessments more quickly as well, along with forecasting. So the majority of the AI models right now are going to be able to provide us a significant speed up in the future.
Oh, that's wonderful. Thank you. And Andrew, what are some of the critical design challenges or constraints that your digital engineering approach will actually help us address?
Yeah, so when you have complex systems like Artemis as an example, or ISS, with a variety of subsystems that all might be provided by different vendors, each one is kind of bringing a piece, but it's difficult without a full integration of these pieces to understand how one piece relates to another and how you might optimize the overall system to take advantage of the different capabilities or constraints. So being able to represent those digitally and be able to run a myriad of trade studies with different kinds of scenarios or different types of inputs can give you significant insights prior to building. Again, writing expensive code or bending metal, building the hardware and integrating it. Even better if you can give out guidelines ahead of those acquisitions to those vendors so they can work to a standard like SysML as an example, or whether you standardize on a tool or standardize on a methodology, being able to provide that in advance so as they deliver those pieces back, you got a much easier time of integrating those and then to be able to conduct those kinds of system of systems studies and analysis.
Yeah, so you take that one step further, and one of the challenges that we face in all of the design is really looking at an integrated approach to cost, schedule, risk, and requirements management. And how is what you're doing here able to manage that digitally?
Yeah, so we've had some success at tying kind of some of the standard cost models together with some of these. If you think of your architecture model, in this case Cameo that we were using, is your source of truth, right? So all of our performance models will pull data from that. It describes your system, describes your architecture. So cost is just another variable in that, right? To be able to kind of, as you start to define your system and you have lines of code and amount of hardware that drives your costs, you can start to find out which elements of your system are driving you. Do the same with risk and can do the same with schedule. If you know that there are certain things that are going to take a long time, you can start to trade those off, saying, hey, what's more important, that I deliver something by this time because of some constraint, or that I deliver all of what I need, but I've got a little more time to kind of do it. You can play those trade-offs by having all those things kind of related in a model and do some optimizations that take advantage of those relationships to deliver more integrated sort of perspectives.
Yeah, and one of the challenges that we have to using any of these kinds of digital tools is getting people confident, enough to use them. So there's a difference between having accessibility to these tools and acceptability to the tools. So getting to a place where you have confidence in the accuracy of these digital twins, I mean, how are you addressing the challenges associated with getting accurate digital twin capability?
Yeah, I think that's a really difficult problem, just because
Yeah.
a lot of the data that we're working with, especially from the global climate models and even from some of the satellites, is often at a very, very low spatial resolution, or it's at a low temporal resolution. And so, we really look to be able to use these algorithms to create a product that's more highly granular, but the trustworthiness of that is the difficult part, right? And I think that was one of the questions earlier, bringing in data from either NGOs or industry into what the government provides. But when it's being disseminated to the public, you have to be careful with that, because that's the difference between operational and R&D. So I think working with NASA and NOAA and kind of creating this partnership to get their stamp of approval from the scientists on it is what we should strive for.
Absolutely. So I'm going to open it up to the audience here for questions. We've got a question over here. Mackenzie. Hi.
Mike's coming down.
Let's let Mackenzie go first. Thank you. So my question is for Andrew. And Crystal, you read my mind on the cost and schedule issue for sure. Yeah. So I'm curious, the state of the tools right now for digital engineering, MBSE, how confident are you that those are ready for a really complex system like, say, JWST? Right? If we were at the beginning of the project and we said, okay, we're going to start out with MBSE and digital engineering for a really complicated system of systems. Are the tools there yet?
It's a great question. So some of the programs that I have managed and had teams do some of this work for they've been quite complex programs. And one of the terms that I like to use to describe that is multi-resolution modeling. You model at the level of resolution or level of fidelity needed to sort of answer the need. There's a tendency and a desire. Modelers like to model, just like surgeons like to cut, right? So when you've got we've got a tool, they like to build models, right? Without the right kind of guidance, it's easy to just let them kind of run wild and then have kind of schedule and cost overruns. But starting at the beginning, saying, here are the outcomes that we want. We want to be able to generate documentation at this kind of a level. We want to be able to answer these kind of questions. We want to be able to cost it at this level based on your work breakdown structure. You can sort of limit your modeling, like the modeling we did here. We had it probably took maybe about a month or so, several weeks of modeling in the Cameo level to get to where we felt we had enough detail to be able to do that. So it didn't take a lot of time. You saw the kind of breakdown that we had of it. You could easily spend years, right, going into excruciating detail, and for some parts you might need to answer certain questions. If you've got a really risky interface that you're really concerned with, you might want to add some fidelity there to be able to represent and do some trade studies there. But in many cases, it's about completeness across the architecture versus deep fidelity in every element. So being artful about how to do that can really help to make that a more manageable problem.
Great.
Okay, thanks for the panel. My name is Stephanie Getty. I'm the Director of Solar System Exploration Division at Goddard. I love, Andrew, this question is for you. I love the tool that you showed with the Artemis case study there. Of course, as the home organization for LRO, I'm a big fan of LRO. Of course, it only gets down to about a ½ meter. Of resolution. And so I think ultimately for hazard avoidance at the astronaut scale, we'll want to integrate not only new orbital capabilities, but also in situ observations that the astronauts are making. And this really folds into how our scientists are thinking about orbital scale to in situ from the ground scale. So can you talk about the process for how you can operate, how you can update and optimize the tools maybe in real time as exploration is happening, and how amenable are the tools, do you think, to those updates?
Oh, another great question. I think the ability to, the data sets ultimately are databases, right, that can be updated with the best data available. So I think with some simple techniques of being able to capture and log data from sort of on-site in situ analysis and being able to transmit that back to the repository that's kind of carrying the data for the rest of it, and with some simple algorithms to essentially stitch that together to create that additional resolution needed in areas, I think is a very doable problem. I'm not directly involved with that kind of a problem today, but I could imagine that is a relatively straightforward thing to be able to do a level of update sort of as you explore, that you could just update those sections. Think of it almost as a grid. Certain grid points or grid sections are going to be more high resolution based on areas that have been explored, and then ones that haven't yet been are going to be based on whatever LRO provides. So being able to selectively sort of add resolution to grids as they're explored, I think is a very doable part of it. I don't know if that answers the question.
Okay, great. Any other questions from the audience? Okay, while we're waiting for him, I'm going to ask Lynn a question here. So how do you validate and ground truth the digital twin models against real world observations?
Yeah, so right now, as I showed, what we're using as ground truth is the GFS, just because that's the closest thing that we have to a global data set in order to ground truth. And it's an operational data product that NOAA puts out that's used for forecasting. We're also planning to look at some ground-based observations in order to pinpoint areas of interest to validate that as well.
That's good. Thank you. All right.
Hi, I just had a follow-up question. I wanted to kind of understand some of the unique challenges that perhaps either of your models had with either scalability, API. I was very interested in the presentations. There's a lot of good there, so I was kind of curious if you can share some of the challenges that your teams had to overcome.
Yeah, there's certainly been a lot of challenges thus far. Yeah, I'd say one of the main ones is certainly scalability. So we're currently using AWS, and we're prototyping it out for a few different variables that we showed. But when it comes to thinking about moving this operationally, which again, we're only building a prototype right now, moving this to terabytes or petabytes of data is going to be certainly difficult with the processing and the resources that would take in order to do it. So that's a main challenge that we're trying to provide recommendations for, as well as costing and planning for NOAA. And I guess, yeah, just a lot of the data some of it's hosted on S3, so it's super easy to get on the cloud, but other times it's way more difficult to get because it's on, websites that sometimes even professors host. So being able to pull all of those disparate data sources together into this kind of one-stop shop has certainly been a journey.
I'll say in our case, we don't have this sort of data problem currently that Lynn has with what she's doing. A year ago, I started doing some of these kind of demos at National Space Symposiums, where we kind of the first one, and we had multiple kind of Alienware laptops and switches and routers and screens. It was about a half-day setup. Now I can just walk in and just plug in it. Now that it's running on AWS Cloud, GovCloud in our case. So that the integration that's all done in the cloud, the resources that AWS provides was a huge factor for us, and so we've not yet seen that kind of a problem of scale. Now back to the previous question, if you get really complex systems, then you're talking about the scalability of some of those tools like Cameo and MATLAB and others. But so far, for some pretty complex tools that we've done, we've been able to run sort of this kind of simulated environment without scaling problems. So fingers crossed, so far it's not been an issue for us.
All right, and so for those people who are not necessarily there yet when it comes to utilization of these, as we talked about before, a difference between accessibility and acceptability. Do you believe, what do you believe are the challenges, risks, et cetera, associated with becoming too reliant on using these digital tools or digital capabilities?
Well, nothing takes a place of just common sense and good engineering judgment
Yeah.
and using either other proven models or real data to validate what you're doing.
Right.
It's easy to fall into the garbage in, garbage out and not really know it if you're putting too much trust and just sort of let your brain, it's a little like using GPS without thinking about it. It's going to take you off a bridge and you're sort of not paying attention. So the capability is there, it's powerful, but it doesn't relieve us of the responsibility to check and double check and validate against other known sources of truth and valid data.
Yeah.
Yeah, I'd absolutely second Andy. I mean, just, use sometimes weather forecasters say LOTW, just look out the window. Sometimes if you want to see the weather, you don't necessarily need to look at your phone. So
Yeah.
yeah, just using common sense and making sure that you're validating, even though we want to kind of move away from these more traditional models that take a long time to run, they've run for a long time and they're generally pretty accurate. So verifying with those and using ground truth data to check your models to create that accountability is key.
Right. Okay. Any other questions before I jump in with another one? We have Krista has one back there.
Okay, well, let me ask an online question,
yes,
and
thank
then
you.
I'll run this up to Krista.
Okay.
So how feasible would it be to create a digital twin model for all existing satellites?
Wow. All existing?
So I'll take that. I've been doing satellite modeling for a long time. It really gets, it's a little bit of a loaded question, but it would depend on what the purpose is for. If it's just for awareness, there are models, sort of space surveillance kind of models that have like all space objects cataloged. If its purpose is like Earth coverage, if they're looking at the Earth, that's pretty doable. If it's the communication side, if it's, so it really depends on kind of what you're doing. There are normally the way this works is you can either have massive amounts, tens of thousands of objects doing a small amount or a single thing that you're interested in, or a handful of things that you're looking at great detail about what they're doing. So it can be difficult generally just from a time as well as a computational standpoint to do all, both wide and deep in that. And then you have to ask yourself, what am I doing it for? Mm-hmm. So usually let your outcomes drive not only what you model, but how much detail you put in those models to get at your kind of desired place to be.
And realistically, when you say all satellites that are out there, that includes other countries and everything else. So yeah, not realistic.
Yeah, I'd agree with use case on that, certainly.
Krista,
Ready? Okay. Yes, hi, this question is for Lynn. So I think there is a huge effort on data assimilation development right now. And at the same time, there's also physics-based AI, right? So what is the vision for convergence of these two efforts? Because at some point, I mean, there's already reanalyses that do assimilate many satellite and other types of data. So how will these converge, and where will your efforts feed back into this broader effort?
Yeah, that's a difficult question, but and this is from my perspective. I don't work for NASA or NOAA, so they may have a broader vision for that. But at least within our program, we view this as a platform that's able to kind of combine these observations in order to create that more like granular data set, kind of similar to reanalysis, right? That would be able to help with prediction efforts. So that's where we see it. It's not meant to take away from data assimilation or numerical weather prediction there. It's supposed to be a support. And yeah, I think that we'll just see how NOAA would want to integrate that into their systems in the future.
all right. And so we are at time almost. We have one more minute. So I'm going to just take advantage of just having this one more minute. When it comes to AI, we talk about ethics, privacy, et cetera, those types of things. And the kind of models that you all are talking about are pretty much, pretty much open for the most part. But you do have human elements to this. And so how are these digital twins and these models taking that kind of thing into consideration?
Well, let's see. So if it comes, part of what we've built is the ability for humans to interact with the models that allows, there's all kinds of work out there in the community about creating models of human behavior to kind of feed models. But in the case where you can have actual humans, that's in some ways better, right? A human will do things, make decisions that a programmed model wouldn't necessarily do. In the area that I'm working so far, and I won't speak for Lynn in terms of her area, but the areas of AI that we are kind of looking, you saw, like, for example, picking optimal paths back.
Yeah.
We haven't really gotten into the point where there's going to be sort of ethical dilemmas related to AI in our space yet, but I can easily see where, and we've seen in just the global community, where it raises questions, and we have to understand kind of where the programming comes from that goes into that, because those are
Right.
people, right, making
Absolutely.
their assumptions kind of get ensconced in whatever models are there, and so it's some of them coming back. But we certainly have to be careful about that, and and I think the transparency comments from the last panel were spot on. Just what exactly is going in, so we can understand better what's coming out.
Perfect.
Yep, similar answer here in the sense that data provenance is a large part of what we do, especially with AI models, of being able to trace back what specifically did you input into this, what specifically did your algorithm do in order to output something, especially for, a decision-making product. Like Dr. Voles earlier was talking about, providing tornado warnings, 5 minutes versus 20 minutes in advance. So if those products are being output and disseminated to the public through an AI model, being able to trace back exactly how that was produced is vital and huge to make sure that there are no issues with how that's being done and that it's trustworthy.
Exactly. Well, thank you all so very much. Please help me thank these panelists for joining us today. Thank you.
Thank you to our excellent panel and the demos of that amazing technology. Hi, my name is Alan Chamerliski. I'm currently an undergraduate student here at the University of Maryland, majoring in aerospace engineering. I'm originally from Crofton, Maryland, and I look forward to a career in the space industry. We'll now take a short break with snacks and beverages in the atrium and more demos for you to try out. I definitely recommend the VR perspective of the spacecraft going to Titan. Enjoy the networking and build new connections. Please come back in 40 minutes for our next session, Lunar Surface Science. Thank you.